Okay, to start this lecture, I have an interesting question for you. Table salt, NaCl, that you put on your French fries. Sparkling, shiny diamond jewelry. What do you think those two have in common? Table on your French fries and diamond found in jewelry. What do those two have in common? What do you think? Weird question, huh? Well, they both are solid objects that have tiny crystals. That's what they have in common. Now, what are crystals? What are crystals in chemistry? Crystals are basically made from atoms or a group of atoms that are arranged. So atoms that are arranged in a 3D pattern that is very ordered. Okay, so we have atoms or a group of atoms that are arranged in a 3-dimension pattern that is very ordered. Now, when I think about crystals, the word that I think about is symmetrical, because the shape of a crystal is very symmetrical. So think about this, picture this, that these atoms that are inside a crystal, they're beautifully packed in together in this symmetrical geometry. So far, so good? Okay. Now that you know what the salt on French fries and diamond jewelry have in common, the next thing to talk about is crystal lattice. What is crystal lattice? Again, the crystal lattice, what they call is the arrangement of these atoms, right? These atoms that are packed in a crystal. The arrangement of these atoms in a crystal, they call that a crystal lattice. So nothing fancy at all. So we have these atoms that are packed in together in this beautiful symmetrical geometry, and we call that a crystal lattice. That's the arrangement of this atom in a crystal. So far, so good? Okay. Now, the last terminology to learn is unit cell. Okay. Now, what is unit cell? Unit cell is the smallest part of the crystal lattice. So far, so good? Okay. Now, let me give you an example of a crystal lattice to see how beautiful it is. There we go. Pretty beautiful, isn't it? So as you can see, atoms are packed in together very nicely, very ordered in a symmetrical geometry in this crystal lattice. And then the smallest part of this is a unit cell. Now, of course, we need to learn about unit cell. Okay, so let's go over what are these unit cell. So there are 3 types. We have simple cubic, we have body-centered cubic, and we have face-centered cubic. They do have an abbreviation. I want to mention it right now. So for the body-centered cubic, they call it BCC. And for the face-centered cubic, they call it FCC. And what I'm going to do, I want to give you an overview of this, and then we're going to go over each one in detail. But each cube represents 1 unit cell. So each cube represents 1 unit cell. So far, so good? Okay. Now, if you have a simple cubic has 1 atom per unit cell. BCC has 2 atoms per unit cell. And FCC has 4 atoms per unit cell. And I'm going to go over all of this in detail and show you how, but I wanted to give you an overview first. Now, the other piece of information that we have to care about is coordination number. Now, what's the coordination number? I'm usually write it as CN, abbreviation. Coordination number is basically number of atoms attached to a single atom. Coordination number for simple cubic is 6. That means an atom is attached to 6 other atoms. For BCC is 8. What that means is a single atom is attached to 8 other atoms. And for FCC is 12. Again, that means a single atom is attached to 12 other atoms. So far, so good. Okay. Now, the other thing that we have to talk about the volume efficiency. Now, what is that? For BCC, the volume efficiency is 52%. Now, what that means is, the atom is going to occupy 52% of this cube. So 48% is going to be empty. Not very efficient, right? For BCC, the volume efficiency is 68%. So that means the atoms are going to take up 68% of this cube, and then the 32% is going to be unused. The FCC, the volume efficiency, is 74%. That's pretty efficient, huh? That's much better. So only 26% is going to be empty space and not used, and the atoms are going to be packed into 74% of the cube. And this is very nice. That means the atoms are packed in there pretty nicely and taking up 74% of the volume. So far, so good? Okay. Now, the last thing to talk about is edge length. So what we're going to talk about, we're going to talk about each side of the cube. And I'm going to put X for that. So this is a side of the cube. This is a side of the cube. This is a side of the cube, right? These are the edge length. Side of the cube, side of the cube, side of the cube, right? Those are the edge length. And for simple cubic, the edge length is 2R. For BCC, the edge length, again the length of the X, right? I just showed you guys, that's the side of the cube, is 4 over square root of 3 times R. And then for FCC is square root of 8 times R. Okay? Now, what is R? What R is atomic radius. So R is atomic radius, right? You know from geometry, you know what radius is. So this is a radius right here. This is a radius, right? The radius of a circle, you guys know that. And this one over here, this would be a radius. This one over here, this is a radius. This is a radius. So far, so good. Now, how about this one over here? If I have this, that would be a diameter, right? Diameter is 2 times the radius. This one here as well, if I look at this one, this is also a diameter. So it will be times 2 times the radius. Okay, you know the radius, atomic radius. So far, so good. Okay, so, and these are the edge length. And I'm going to talk about this one by one in a second. Now, but really quickly, because it's easy to show for a simple cubic, you can see how the edge length, the side of the cube is equal to R, right? I have an R and I have an R. The other one is a little bit more complicated, but a simple cubic, you can see the 2R right here. That's why the X is equal to R. So far, so good? All right. Now, this is an overview, and I want you to have this in front of you, especially the edge length. I want you to make sure you guys remember this for me. Now we're going to go over each one to kind of get into that, to see how these numbers came about. First one is a simple cubic. Let's talk about simple cubic. And I actually drew a cube here for you. I attempted to draw a cube. It took a few tries to draw this one. Now, each corner each corner of this cube, how many corners do we have? I want you to count it for me. Count it. 1, 2, 3, 4, 5, 6, 7, 8, right? Each corner is 1/8 of an atom. So each corner is not a whole atom, is 1/8 of an atom. So 1/8 of an atom. Now how many corners do we have? We have 8 corners. So 1/8 times 8 would be 1. So that's why we have 1 atom per unit cell. Here I say we have 1 atom per unit cell. Now you know how we came up with that. Because each corner is 1/8 of an atom, and I have 8 corners. So then when I add them up, it will be 1 full atom. So far so good? Okay, beautiful. Now, for the sides of the cube, right? We have a side of the cube, we have a side of the cube, we have a side of the cube. We said the edge length is what? The edge length is 2r. And you can kind of see this because this is a radius. This is a radius and this is a radius. And you can see this corner, this side of the cube, this edge length is 1r, So it's 2r is going to be my edge length. Yeah? Okay. Now here is a question. I'm going really slow. Hopefully you guys are following me because you probably haven't seen this before. Volume of a cube. What's the volume of a cube? Volume of a cube is length times width times height. You guys remember that? Yeah. Length times width times height is a volume of the cube. And in this case would be x times x times x, right? So the volume of the cube is going to be x cubed. That's going to be the volume of the cube. I need to remember that. So far so good? Okay. Now, I also need you to remember that, so the volume of the cube is going to be x cubed because the width and the length and the heights are going to be multiplied together. That's how you get the volume of a cube. And each x is 2r. And each x is 2r. You follow me so far? Okay, beautiful. Now, here's what we're going to do. And this is really cute. The volume of an atom over the volume of the cube. Okay? We're going to divide those together. Now remember, an atom is spherical. Right? Atom is spherical. And sphere has a volume. And to calculate the volume of a sphere, you would be 4/3 times pi r cubed. Again, how did I get this? I just looked up. How do I calculate the volume of a sphere? If you Google the volume of the sphere, this is the formula you get. Okay? So far so good? Alright, one more time. I'm trying to figure out the volume of an atom. An atom is spherical. And the volume of a sphere, this is a formula to figure out the volume of a sphere. So I can figure out the volume of an atom. And remember, how many atoms do we have? We have 1 atom, right? Write it down. Because we have 1 atom per unit cell. Now, volume of the cube. What's going to be the volume of the cube? We say it's going to be x cubed. X cubed is going to be the volume of the cube. You agree? Okay. So, I have 4/3 times pi r cubed over. Now, we know what x is. Each x is 2r. Each x is 2r. So, what I'm going to write down, I'm going to write down 2r and then cube it. I'm going to mention this again to make sure I haven't lost anyone. So, this is the volume of the cube is x cubed because it's length times width times height. But I know that each x is 2r. So instead of x, I'm just going to put 2r and then cube it. Yeah? Okay. Now, what I'm going to do now, I want to, nothing fancy. I'm just going to simplify this a little. So 4 over 3 pi r cubed over, and then this would be 8 r cubed. All right. Now what I want you to do, I want you to cancel out whatever you could cancel out. What could you cancel out? Yeah, the r cubed, you can cancel it out. Now it doesn't seem that bad, does it? Now you can just I can't do math in my head, but with my calculator, I can go 4 divided by 3 times pi, which I would get 4.1888 over 8. If I do that, what I end up getting is 0.5236. That is so cool. Hold on, you're going to see why this is so cool. Multiply that by 100 to get percentage. That would be 52%. Now, what did we say? Whoa! Ready for this? That's pretty cool, right? We said that volume efficiency for simple cubic is 52%. How did they come up with this number? Well, you just did it too. You came up with this number as well. So 52% efficiency, which is not great, right? The atom is occupying 52%, 48% is empty. So not the best efficiency. So far, so good? Okay, beautiful. Are you ready for next one? Let's go for the next one. Next one is body center cubic. Yeah, I had to draw this beforehand because otherwise I would spend 10 minutes of this lecture trying to draw this out. Body center cubic, or BCC. Now, if you remember, we said there are 2 atoms. Now, let's go how that comes about. Now, again, remember, I showed you guys that there are 8 corners, right? I showed you that there are 8 corners. And we said each corner is 1/8 of an atom, right? A cube has 8 corners. I showed it to you guys that. And then I can even show it to you guys again. So we have 1, 2, 3, 4, 5, 6, 7, 8. 8 corners times 8, okay? Plus, now what do you have over here? Look at this. You have 1 whole atom in the middle. So plus 1. Again, how did I get this? Right here. You have 1 whole atom in the middle. So each corner is 1/8 of an atom. 1/8 times 8 is 1. Plus, I have 1 whole atom in the middle. So if I add them together, I have 2 atoms. And that's what we said. We have 2 atoms per unit cell. Yeah, you guys are good so far? Okay, beautiful. Now again, and also remember what we said. We said the edge length, okay, we said those are x. And then what we said that the edge length, which was x, was 4 over square root of 3 times r. You probably look at that and you go, whoa, this is crazy, right? It was easy to see for a simple cubic because it was r times r, so you have 2r would be the edge length. Now this one is a little bit harder. We're going to go over how they came up with this crazy formula for this. You guys ready for this? All right. Pay attention to this. It's not bad. I'm going to walk you through it. Now, I'm trying to look at from here to over there. This is what I'm interested in, okay? This is what I'm interested in to figure out the edge length of a cube. This is what I'm interested in. Now, if you remember, and we just went over that over there, let me draw it in a different. So what we have in the middle, we have a, let me draw it one more time. This is why I had, oh my goodness, this is why I draw those cubes beforehand. So in the middle, we have an atom, right? And then each corner is 1/8 of an atom. So far, so good. So each corner is 1/8 of an atom. And in the middle, I have one whole atom. Yeah, you guys following me so far? Okay, beautiful. Now remember, this is R. Yeah, radius. This is R. This is atomic radius. And this one, this is a diameter. So this is 2R. That's a diameter. So it's a 2R. So the length of this diagonal, is 4R. Because I have R, R, and I have 2R. Okay. So the length of this diagonal is 4R. You guys are following me so far? Okay, again, because I have one full circle here, that's 2R, I have R, R, so the length of this diagonal is 4R. Alright, now, what we're trying to figure out is not the length of the diagonal, it's the length of the edge length, right? Is the edge length is what we're looking at, so keep your eye on the ball. Now, here is what I'm going to do. Now, remember again that what I'm trying to do, I'm interested to connect these 2 points. This is what I'm interested. I need to connect these 2 points. Now, let's focus on the diagonal on the bottom of the cube first. Okay? That's this one right here. So we're going to focus on the diagonal on the bottom of the cube. And what I'm going to do, I'm going to call that L. Okay? Now, what I have a right triangle, don't I? I do. I have a right triangle. That's interesting. And of course, remember, this is x and this is x. So I have a right triangle, Pythagorean Theorem. You guys remember that? Yes, you do. Pythagorean Theorem. So what does that mean? That means that the L squared is going to equal x squared plus x squared. Okay? So to figure this, I have a right triangle, the Pythagorean Theorem, L squared equals x squared plus x squared. We're good so far? Okay. So again, we just focus on the diagonal on the bottom of the cube. Okay? But again, keep your eye that we're interested to connect these 2 points. Now, we had this and we call that L. Now, what I'm going to do now, I'm going to draw from here to here. Okay, let me do it. Yeah, this is drawing. Hopefully you're drawing it with me. So you'll see it's not almost went there. One more time. Ready? Okay, cool. All right. And again, remember, this is x, this is x, this is x. Now, what do I have again? I have another right triangle, right? I have another right triangle. Okay? So this is great. So now I'm going to call this one D. I want to call that one D. Pythagorean Theorem again. So it would be D squared would equal L squared plus X squared. Do you guys agree with that? Again, I have a right triangle. D squared is going to equal L squared plus X squared. Yeah? Okay. I'm going to take a step back because I want to make sure you understand this. You don't have to read this on your own. We're going to come back over here. Over here, first we focus on a diagonal on the bottom of the cube. And if you have this diagonal over here, you'll see that you make a right triangle. Think about geometry, right? The good old days in high school math. So you know that this is a Pythagorean theorem. The L squared equals x squared plus x squared. Then I'm going to come over here and say the 2 points that I'm actually interested in is here to here. I'm going to draw that diagonal over there. Okay, so I draw this diagonal over here. Now I still have a right triangle. So this diagonal, which I'm going to call it D, so D squared would equal the L squared plus the X squared. Again, I have a right triangle, Pythagorean theorem again. d squared is going to equal L squared plus X squared. Yeah? Okay. Now, what I'm going to do, I'm going to sub for L squared. What can I sub for L squared? I can sub X squared plus X squared. Do you guys agree? So d squared is going to equal, instead of L, I want to put X squared plus X squared. And then I have an X squared here. So what I did, I just subbed for L squared, I subbed this one over here. For L squared, I subbed this over here. Okay, so far so good. Nothing fancy at all. So 1x squared, 1x squared, 1x squared. What would you get? That means d squared is equal 3x squared. So far so good. Yeah, I'm going to go over all the math to make sure you guys are following me. Now what I'm going to do, I want to take a square root of both sides. If I do that, then what would I get? What I would get d is going to equal square root of 3 times x. This is looking pretty good, right? This is looking not bad at all. Now, remember what we talked about. So this d over here is a diagonal. What was the length of the diagonal? What was the length of the diagonal? It was 4r, wasn't it? Yeah, this d over here, this was the length of the diagonal. And then if you look over there, the length of the diagonal was 4r. We already figured that part out. That's pretty cool, right? So instead of d, what can I put? I can put 4r. So instead of d, I'm going to put 4r is equal square root of 3 times x. Okay? So now it doesn't seem that bad at all, does it? No. Then what am I going to do? I'm going to divide it, by 4. Okay? I'm going to divide this by 4. Now, if I divide this by 4, then I'm going to get r is going to be equal square root of 3 over 4 times x. That is pretty cool, right? Because this one matches what we had. This one matches what we had. Yeah? Okay, so now you know how they got the length, the edge length for BCC. Are we good so far? Okay. Now let's figure out, the next part I'm going to figure out is the volume efficiency. And I'm actually going to go over this one pretty quick because I feel like you know the volume efficiency already, right? You know the volume efficiency based on this simple cubic. But let's go over it quickly. You ready? Let's do it. You can probably do this easily, but let's go over it anyway. So the volume of the atom over the volume of the cube. You want to figure out the percent efficiency and see if it matches up, right? Now the same thing as before, the volume of the atom, we're going to look up the volume of sphere, right? Because atoms are spherical. So the volume is 4 over 3 times pi r squared. That's just the formula to find the volume of a sphere. Now here's the thing. How many atoms do you have per unit cell for BCC? You have 2 atoms. So then you have to times it by 2 because you have 2 atoms. Before it was just 1, but now we have 2 atoms, so I have to multiply by 2. So far so good. Okay, now remember, this is a cube. The volume of the cube, as the same as before, is x times x times x. Is the length times width times height. So it's x cubed. And now you know what x is. What x is, x now is 4 over square root of 3 times r. Do you agree? Okay. Now all I have to do, I have to cube it. You can follow me so far? Okay, again, nothing you've never seen before. And I'll let you do the math, multiply it out, cancel whatever you can cancel. When you do this, what you end up getting, you end up getting 0.6802 times it by 100, you get 68%. And that's what we got before, that BCC has a 68% volume efficiency. And now you know how we got that. Pretty cool, yeah? Okay, are you ready for the last one? Let's go over face center cubic, FCC. All right, here is our FCC. Now, these are the edge lengths. Now, FCC, the same as before, okay? If you remember, we said that each corner it has 1/8 of an atom, right? Each corner has 1/8 of an atom, and you have 8 corners for a cube. You have 8 corners for a cube, and each corner is 1/8 of an atom. Now, plus, do you see these ones? Yeah. What those are? Those are actually, they are half of a sphere. So you can see 1, 2, 3 here, but these are not one full sphere, it's half of it. So now 1, 2, 3 you see here. So you see 3 half a sphere. It's not a whole sphere. But how many sides does a cube have? Think about it. If you have a cube next to you, look at it. Cube has 6 sides. Do you guys agree? So cube has 6 sides. And so what I have 6 of these. So I have 6 of these. But again, there are half of a sphere. So half times 6, if I add them up, I end up getting 4 atoms. So that's how we got 4 atoms per unit cell. Okay, so far so good. Again, each corner is 1/8 of an atom. I have 8 of them. Times 1/8 times 8 is 1. Now I have 6 of these. You can only see 3 here, but each side has half a sphere. And then if I add that one, add it together, 4 atoms per unit cell. Okay, beautiful. Now let's go over edge length and how we came up with that equation. Now if you look at the cheat chart that I showed you at the beginning, it said that the edge length, square root of 8 times r. Let's go and see how that came about. This is actually not bad. So what I'm going to do to make it easier, I'm going to have a side view over here. Okay. So again, what this is this one right here. Now, if you remember, we said that this was an r, this was an r, and this was 2r. Yeah. The radius, diameter, because I have now that would be 2r. Okay, so what I have here, if you look at this, over here what I have 4r. So what I'm going to end up having here, I have 4r, right? Because again, I have r, and then 2r. So this whole diagonal over here, it will be 4r. Okay, probably you can see where I'm going with that. Yeah. So you have a right triangle again. You have a right triangle again, don't you? Yes, you do. So I have x and I have x here. So Pythagorean Theorem, nothing we haven't seen before. Now what is that going to tell us? What that's going to show us, that's going to tell us that 4r squared equals x squared plus x squared. Yeah, so right triangle, Pythagorean Theorem again, x squared plus x squared equals 4r squared. Now, so 4r squared, that would be what? That would be 16r squared, and then 1x squared plus 1x squared would be 2x squared. Okay, you guys following me so far? Okay, that's not bad so far. Now, what am I going to do? What I'm going to do, I'm going to divide this by 2. If I divide this by 2, what I'm going to get, I'm going to get 8r squared equals x squared. Now what am I going to do? I'm going to take a square root of each side. If I do that, what I end up getting is going to be x is going to be equal square root of 8 times r. That's really cool, right? You did this probably all on your own, and then this matches the edge length that we used to get. Yeah? Alright, not too bad. Nice job. Alright, so last thing to do to convince ourselves about the volume efficiency. Again, we're going to do this one quick because you know this by now. The volume of an atom over the volume of the cube, right? And then if we times it by 100, we expect to get about 74%. You should do that to convince yourself. Again, the volume of an atom will be the volume of the sphere, which is 4 over 3 times pi r squared. Now, here's what this is interesting. Remember, how many atoms do we have per unit cell? We have 4 atoms. So I have to times it by 4. That's the only thing that is you have to pay really attention to, that we have 4 atoms now. So the volume of one atom would be times 4 over, okay. Now, I know that the volume of the cube is going to be x cubed, and my x, square root of 8 times r, and I'm going to cube it. You guys follow that? One more time. Because x times x times x would be the volume of the cube, and my x is square root of 8 times r, so square root of 8 times r, cube it, and that would be the volume of the cube. And now, if we do that, and you times it by 100%, you should get around 74 efficiency, and you'll see that you will get that. So far, so good? Okay, beautiful job so far. Now what we're gonna do, let's do some practice problem to see how you would do this when you do a practice problem. Ready for first one? Alright, you got this. You can take a break if you want and then come back, but let's do a couple practice problems to show you what you will do with all these numbers and what I've shown you. Okay, here is our first practice problem. Now, if you look at this, the practice problems are really not bad. To do problems with unit cell, they're really not bad. Now, here's the key to do well. Unit conversion. Unit conversion is key. You do the unit, you remember the unit conversion and keep track of the units, and you're gonna be okay. So far, so good. Now, in this place, when you read a problem, write down, underline what the problem is giving you. They're giving you the density, grams per ml, and they're giving you the cell edge length, okay? The unit cell edge length, that's given to you. And they're asking you, what type of unit cell do you have? Do you have simple cubic? You have BCC? You have FCC? What do you have? Now, remember, to know what type of unit cell you have, the key is figuring out the number of atoms. Do you agree? The key is figuring out the number of atoms, because if we figure out the number of atoms, then we'll know what type of unit cell we have. So far, so good? All right. Now, let's do this one together. So, I am given density. That's cool. Now, what is the density? The density is 7.87 grams per ml. Right off the bat, what I'm going to do, I'm going to make it centimeter cube. Why did I do that? Because later on, when I have the edge length, which is in picometer, I need the centimeter is going to help me, not so much the milliliters, right? I need length. I need centimeter. So that's the first thing that I did. So the first thing I did, remember, because if you remember from Chem 1A, 1 milliliters is equal 1 centimeter cube. And that's the first thing I'm going to do. I want to say 7.87 gram over centimeter cube, because 1 ml is 1 centimeter cube. So far, so good? Okay. Now what I'm going to do, gram is not going to get me anywhere. What is going to get me somewhere is atoms. What I want atoms, right? Because remember, number of atoms per unit cell would tell me what type of unit cell I have. So atoms is what I'm looking for. If I have gram, can I go to atoms? Yes. You know, remember your Chem 1A. because I can go gram to moles and moles to atoms. So 1 mole of iron, if you look at the molecular weight, is 55.85. That's great. So now what I can do, I can cancel out the gram, because gram to moles, I use molecular weight, you know that. Now, how do I go from mole to atom? Avogadro's number. 1 mole is 6.02 times 10 to the 23rd. So far, so good. If I do this, I get 8.4829 times 10 to the 22nd atoms per centimeter cube. I like this. Why do I like this? I like this because I have atoms, and atoms I can do stuff with. All right. Then I'm going to say I have 287 ppm. I don't like that. I like centimeter, right? Because right now I have atoms per centimeter cube. So let's convert that to centimeter. Picometer go here. Centimeter goes on top. Centimeter is a larger unit. So 1 centimeter is 10 to the 10th picometer. When I do that, I get 2.87 times 10 to the minus 8 centimeter. That's great. Now, what is this? What this is the edge length. So this is my x. This is the edge length. This is the x. Now, do you remember what we talked about? How do you figure out the volume of a cube? How do you figure out the volume of a cube? We talked about it. Is height times length times width, so it would be x cubed. Do you agree? Okay. Do you have the x here? You do have the x. So 2.87 times 10 to the minus 8, which is centimeter. Don't forget the unit. I'm going to cube that. If I cube that, I get 2.364 times 10 to the minus 23rd centimeter cubed. This is great because I just figured out centimeter cubed. That's the volume, right? That's the volume. Remember, because this whole thing gets cubed, the centimeter also gets cubed. All right. Now, how do we do the last part? You know how I like to do this? Proportion. Every time I have a chance to go proportion, I take that chance. I love setting up proportion. Okay, now let's set up a proportion. Based on what we just figured out, I have 8.4829 times 10 to the 23rd. Hold on. I underestimated how big this number was. So I have 8.4829 times 10 to the 22nd atoms. You agree so far? For 1 centimeter cubed. I want to set up a proportion. Now, what I have, what's it doing? What I have 2.364 times 10 to the minus 23rd centimeter cubed. How many atoms is that? Okay, I'm gonna go over this video in a second after I stop erasing my work. You ready? So, proportion. I love proportion. I don't know about you guys, but every time I can have a chance to do proportion, I take advantage of it. So here's a proportion that we set up. I know that for 1 centimeter cube, I have this many atoms. Now, if I have this many centimeter cube, how many atoms do I have? Yeah? Okay. It's not too bad, not too bad. So what my x is going to be, if I get the x, I'm going to get 2 atoms for x. I'm going to get 2 atoms for x. So what does that mean? If I get 2 atoms, I have body centered. I have BCC. I have body centered. Yeah? Alright, I'm really proud of you guys for hanging in there with me. Really, really, really nice job. Alright, I know you don't want to hear this, but let's do one more. Let's do one more practice problem, yeah? You're game? Let's do it. Let's do one more practice problem, and then you're gonna be able to do the lab worksheet. Okay, let's do it. Here is our next problem. So when you read this problem, what they ask you for, they ask you for density, right? So the first thing I want you to remind me is that what is density? Density is mass over volume, the good old days, right? Mass over volume, that's the density. So far so good. Okay. Now, they also give you, what did they give you? They give you the atomic radius. They give you the atomic radius, yeah? And they tell you that this is a cubic closest packing structure. Now, what is that? We didn't have that one, did we? We did. Remember which one was the most efficient one? The FCC, right? That's the most efficient one. So this is another name for the FCC, the closest packing structure. So far so good. That's just another name for FCC. Okay, so they're asking you for density, right? And the edge length of the cell unit. And then they give you the atomic radius. That's great. And they tell us this is FCC. I know it's FCC because FCC is the most efficient one. And the other name for it is a cubic closest packing. Because the most efficient one, you can pack in a lot of atoms nicely in there. 74% volume efficiency. So the other thing I want to put down for FCC, I know that the edge length, the x is equal square root of 8 times r. Okay? So I know those things. That's great. And the other thing that I know is that the volume of a cube is x cubed. And the x is square root of 8 times r. So those are the pieces of information I know before even I read the question. I know it's FCC. So this is the edge length for FCC. The volume of the cube is x cubed. And this is my x. And I know density is mass over volume. Alright, so now we're going to go back, read the question and see what we have to do. Remember what I said? I said the key is unit conversion, right? The key is unit conversion. Don't forget that. The first thing I'm going to do, I'm going to say, okay, they give us the atomic radius in picometer. That's not going to get me anywhere. What I want to convert it to is centimeter. Because what they want at the end, they want the density to be grams per centimeter cube. Okay, so let's do this. So I have 170. And the other thing that I can, let's actually do that first. 174 picometer. Okay. And I don't want the picometer. So the picometer is going to be down here. I want centimeter. Which one is the larger unit? Centimeter. 1 centimeter is 10 to the 10th picometer. So I get 1.74 times 10 to the minus 8 centimeter. Are we good so far? Okay. And I like the centimeter because I'm going to end up with gram per centimeter cube anyway. Alright, so now I have a centimeter. Now remember that the edge length is square root of 8 times r. Well, the radius is given to me, and I just converted the radius into centimeter, so I can easily calculate this. That would be square root of 8 times 1.74 times 10 to the minus 8 centimeter. Okay, you guys are following me so far? Okay, let's put in our calculator, see what we get. I get 4.92 times 10 to the minus 8 centimeter. We're good so far? Okay, so that is my edge length, right? That is my edge length. Again, don't forget that the edge length is basically the x. The edge length is definitely the x. Okay, so far so good. All right, now I know density is mass over volume. I know density is mass over volume. Now what I'm going to figure out, the volume, because the volume is x cubed and I have x, right? And I have x. So 4.92 times 10 to the minus 8 centimeter, that's my x. If I cube that, what I end up getting is 1.191 times 10 to the minus 22 centimeter cubed. Okay, I got that. Beautiful. So now what I have the volume. So what I have the volume of the cube. Beautiful. Okay, now density is what? Density is mass over volume. Density is mass over volume. This is great. I have the volume, but the other piece of information that I need the mass, right? I need the mass. Okay, we can figure out the mass. Now, how are we going to figure out the mass? Now, remember this, that FCC, we had 4 atoms per unit cell. You guys agree? We had 4 atoms per unit cell. So right here, we're going to do some canceling out. We have 1 unit cell. Okay? We have 1 unit cell. And then we had 4 atoms per unit cell. So we had 4 atoms per unit cell. So far so good. Okay, so then I can cancel out the unit cell because we have 4 atoms per unit cell. I have 1 unit cell. Now I have atoms. Remember what I want? I want mass. Well, how do you go from atoms to mass? You know how to go from atoms to mass. Atoms to moles, moles to mass, to grams. You know how to do this. So I don't want is atoms. I want to convert it to moles. 1 mole is 6.02 times 10 to the 23rd atoms. So far so good. Okay, so I just got atoms, and atoms can cancel out. Now what I can do, I can go from moles to grams. And that's what I want, because density is mass over volume. Density is mass over volume, right? Okay, so now how do I go from moles to grams? Molecular weight. So 1 mole of Pb, what's the molecular weight? Is 107.8 grams. Now this is great. So the moles, oh, that's not great. So the moles cancel out and I end up with grams, which is what I want. Okay, so what happens? Let's put it in the calculator to see what we get. I get 1.3807 times 10 to the minus 21st. Okay, so this is great. This is great. Why is this great? Because remember, density was mass over volume, right? So density was mass over volume. What I just figured out, the volume and I just figured out the mass. I have both. So all I have to do, I have to plug it in. So what is my mass? My mass is 1.3807 times 10 to the minus 21 over, what is my volume? My volume is 1.191 times 10 to the minus 22. Okay. Now remember, you have to care about sig fig at the very end. Don't start rounding up at the beginning. You have to round at the very end. To kind of remind you of the sig fig. You round at the very end. So now I can round. I look at this problem and I am limited to 3 sig fig. So my density is going to be, you ready for this? Is going to be 11.6 gram per centimeter cubed. All right. Okay. So the key to doing these unit cell problems is remembering, first of all, figure out what type of a structure you have. FCC, BCC, you have a simple cubic, and then write down the edge cell, the edge length formula for that. And remember, the volume of the cube is always x cubed, and you always know what the x is because you know the formula for edge length. And then from that, you can just figure out, plug in the numbers, and do unit conversion. The one last thing to kind of keep in mind, remember, what we really need is atoms, right? The last problems, we really need atoms because number of atoms per unit cell tells us what kind of unit cell we have. Grams to moles to atoms. Don't forget that conversion, gram to moles to atoms. And sometimes we have to go the other way. They give us an atoms and we have to go back to gram. And I know you know this, but I'm going to put it over here anyway. You know, this is from back in the days, good old days, grams to moles to atoms. Don't forget this conversion. Have this conversion in front of you, and you should be able to do any problem. All right, thank you for hanging in there with me. This was a long lecture. You deserve to go have some ice cream right now. All right, I will talk to you guys next time. Really good job.